Thank you very much. When does the session start?
Right now.
Right now. Okay. Thank you very much. I'm sorry.
Okay.
See you. Yes.
The live streaming is started, so we can start the session.
Okay, folks. Good afternoon from Brazil, and I think, good morning from Brazil, and good afternoon from Cagliari. Welcome to ICCSA session. I'm Rafael Santos from the Brazilian National Institute for Space Research. I'm going to be the chair of the session GenTrack 5-9. We have 4 presentations starting right now, starting with Luis Pool, Guilherme Weigert, Casales, Helio Cristana Guardia, and Hermes Sanger. Distributed novelty detection at the edge for IoT network security. Are you guys online? Luis, I can see you.
Hearing good?
Yes, I can see you. I can hear you. If you want to share your presentation.
Right now.
We're going to have presentations in more or less 10 minutes. If you can check the time, I will alert you if you're over time. Then 5 minutes for questions.
Okay.
Okay, Luis, go ahead. Thank you very much.
Hello, everyone. I am Luis Pool from the Universidade Federal de São Carlos, Brazil. I'm here to present our work on distributed novelty detection on the edge for IoT network security. Our main motivation was the growth of IoT and associated risks in recent years, such as the record-breaking denial of service attacks from IoT botnets. To address such risks, network intrusion detection systems, especially those detecting anomalies, need to work well in IoT and fog scenarios. To that end, we chose a novelty detection algorithm to be ported in a fog scenario, intending to have a small detection latency without cloud degradation. Our scenario is a common IoT scenario where sensors at the edge communicate via gateways to the public network, internet. Traditionally, the risk is at the edges, and the power to detect such risks is in the cloud. We aim to reduce the detection latency by running the system on small fog computers nearest to the data source. Previous work on this subject includes BigFlow, a system that spans from network flow description extraction to alarm generation. However, this system requires external updates and is cloud only. Another inspiring work is Catraca. It also handles flow extraction to alarm generation, and by using network virtualization functions, can run probes in the fog. However, detection is done in the cloud. Another approach is the IDSA IoT architecture, where 3 novelty detection algorithms are evaluated in a fog and IoT context. However, this architecture does not implement a full system, handling large data. With the state-of-the-art explored, we present the chosen algorithm, MINAS. MINAS is an offline-online novelty detection algorithm that takes a flow of examples and gives examples labeled as known, extension of a known class, novelty, or unknown. To that end, MINAS uses a list of spherical clusters as model and Euclidean distance for the classification test. It also uses k-means and clustering as basis to find new patterns. Our proposal is to employ MINAS in an intrusion detection role in a distributed fog environment, following the IDSA architecture. We also want to observe the effects on classification quality due to the change from sequential to a distributed algorithm. As for our method, we chose a technique and platform for the distributed implementation, and in the end, we increased the fog usage in the architecture to minimize latency and also due to technology constraints. For validation, our experiments were designed with a suitable environment and data set. Also, metrics were chosen for quality and scalability assertion. Our implementation uses OpenMPI and is architected in 2 modules, root and leaf. One node runs the root module, and the remaining nodes in the cluster run the leaf module. The root module has 2 tasks, sampler and detector, while the leaf has the classifier and model receiver tasks. Following the sequencing diagram, Input data is taken in by the sampler and distributed via round robin to each leaf, while the classifier task is run distributed on the leaf nodes. This classifier takes a sample and the current model and assigns a cluster's label. If found, sending the result to the detector. The detector task then takes the labeled samples from the leaves and puts forth this result to the application's output for our next system. The detector task also stores the samples labeled as unknown to execute the novelty detection method when needed, and then broadcast these new sphere clusters to the model receiver at the leaves. The model receiver is used to maintain the leaf model up to date asynchronously. In our experiments, our setup was a 3 Raspberry Pi 3B cluster over Ethernet on the December 2015 segment of the Kyoto 2006 intrusion detection dataset. This dataset was treated and then split in 10% for training and with only normal class and 90% for the test with majority attack class. We chose this distribution to highlight the novelty detection aspect, as our goal is to detect never seen before attacks. For the quality measurement, we use multi-class confusion matrix with novelty label assignment as its derived matrix. For scalability, we use GNU time measurements as we have a fixed size test dataset. So this is the stream visualization for the reference means implementation and the new development, both in sequential operation. In this visualization, novelties are shown as dashed vertical lines with some labels at the top. Those lines show us that the implementation catches, or new implementation catches less novelties, being 9 instead of the previous 12. In this visualization, for each sample in the output stream, the confusion matrix and the derived summary metrics are updated and presented as the horizontal curves. Those curves show us that there is some discrepancy in the implementations, but the observed metrics are roughly the same. For the parallel undistributed versions of the experiment, fewer novelties were detected, but we see no significant change in summary metrics. Again, the main effect we want to draw attention to is the shift for the labels 0 from the 300K mark to the 400K mark in the distributed version. This shift was our main concern when developing a synchronous novelty detection task. As the main classifier is still working, the model is updated, and until the proper propagation of the novel clusters, those classifiers are producing results with an incomplete model. It also shows the behavior of the Minas algorithm, where samples used for new clusters are discarded, even if they could be presented with a more accurate label at the cost of duplicated output samples. Finally, this is the summary of our main experiments. The main takeaways here are the speed up, where we had a maximum of 0.97 with 4 nodes and 12 processors. And also the time taken, where the reference implementation took 2,700 seconds and our test took around 100 seconds to handle the same data test. This is the overview of time usage on the root node per added CPU instance. We can see that the user metric and the system metric tend towards each other at 200 seconds as we add instances. We reason that this is due to computation versus communication limit in our implementation. In conclusion, data stream novelty detection as in network intrusion detection or even system behavior monitoring and analysis on IoT environments is still challenging due to the data volume, latency, and small device constraints. This approach has some success in handling the intrusion detection in this constraint scenario, while the effects of distributing this algorithm cause an impact on the quality measurements, and mitigation of those impacts must be included in further attempts. Our implementation was faster than the reference one. However, good speed up was not found. Further work can be done with other novelty detection algorithms or by changing Minas internals. Other line of work can be done on improving communication to computation ratio or load balancing. So this is our work. Thank you everyone for listening, and I'm open to questions.
Thank you, Luis. We are open for questions. You can either turn your microphone on or camera and talk and ask the question online, or you can use the chat function. So we have some time for questions. Luis, I'm going to start with one. You mentioned that you used the k-means algorithm.
Yes.
It is known as being slow, and as one of the requirements that you have to have all the data in the same memory space.
Yes.
The implementations of parallel k-means or distributed k-means are not really that good. Did you have any problem with the amount of data that you have to distribute using k-means?
Actually, no. As the Minas takes only unknown samples, buffers it in a small segment of memory, and then runs the k-means to detect novelties. Thus, it is slow. However, we can control the buffer amount with parameters on the Minas algorithm. So this task here is sequential on one thread only, and does not distributed. The novelty detection is asynchronous, but not distributed in each leaf node or parallel in each node. We had issues. We could use clustering, which is a better algorithm for this case. However, the implementation was not done in clustering.
Okay. Did you try? Did you consider any other algorithm that used, for example, another problem of the k-means is that you have to provide a value for k, so you have to test for different values for k. And there are algorithms like dbScan and several others that it sort of organizes itself trying to locate for the best number of clusters. Did you try any of that, or is outside of the scope of your research?
We did try other parameters. Let me show you what I'm talking about. On the literature, there is parameters for the Minas algorithm, and we chose some sane parameters. However, we did not do a further optimization to not skew the results towards a better result than it could be. So we try to maintain the reference implementation parameters and the bibliography parameters to the Minas algorithm. One of these parameters is the k for the k-means and the other clustering algorithms to generate novelty to limit how many novelties can be detected on each run of the novelty detection algorithm. However, as I said before, this is limited here by the buffer amount we can use. Other clustering algorithm is the clustering, which, despite the fact that it can operate in a streaming fashion, that is no k necessary, just a key for the amount of memory used, it was not used in this fashion. The Minas uses it in a batching fashion, not a streaming fashion.
Okay. Okay, thank you very much. Folks, do we have further questions for Luis? Okay, if you don't have any further questions, Luis, I'd like to thank you again for your work. Congratulations. And I have to ask for the next presenter. Is that, I hope it's Mr. Pompimol Chaiwood Chisak. I'm not sure about the pronunciation. Is Mr. Pompimol present? No, I don't think so. In this case, we are just going to ask for the next presentation. And we can ask again for the presentation of Mr. Pompimol later. The next presenter is going to be Nikhil Kumar, Vishal Mittal, and Yadavashan Sharma. Are they present? Also not. So let's call the next one. That's Geoffrey Expin, I think he's here, Eduardo Esteves, Saravana Prakash, and these names are fantastic. Tirumuruganandaham. I hope it's like that. Sorry about that. That's an awesome name. This. I think this is fantastic. That's another nice thing about ICCSA. You meet people from all over the world, and you learn a lot of interesting things. So anyway, Geoffrey, are you going to be the presenter?
Yes, okay. I'm going to present our work.
Okay, so Geoffrey is going to present us the paper, Hydrogen Economy and its Production Impact on Automobile Industry Forecasting in Ecuador using Principal Component Analysis. Is that right?
Yes, it is right. Let me know
Okay.
if you can see the presentation.
The sound is a little low, if you can fiddle with that, and we can see your presentation.
Okay, so let's start what we are going to talk about. First, about authors, second, introduction, third, materials and methods used, then the results, and finally, the conclusions. So who are the authors and universities involved? In my case, Geoffrey Spin from Universidad Técnica de Ambato here in Ecuador, Eduardo Esteves from Universidad da Coruña, and Saravana Prakash Thirumuruganandam from Universidad Tecnológica Indoamérica. Okay, what about hydrogen? Hydrogen exists in 75% in universe, and its abundance on Earth too. Other either to organic components like methane forming water, for example. Also, hydrogen is an energetic vector like cells, batteries, and fossil fuels, substance that store energy. It serves as fuel and must be manufactured. Why? Hydrogen is not found in its pure state on the planet. So we have to produce it in a clean way to just having water or electricity that we call renewable energy for transport. Okay, what about hydrogen and cars? Okay, hydrogen will be the future fuel because it does not burn. It generates energy to move an electric motor, and we can consider it that a hydrogen vehicle is like an electric vehicle. So what is the difference? The difference is on how electricity is generated. Hydrogen vehicle use a fuel cell integrated in the car, while electric vehicle receives the electrical charge generated in a power plant. We know about hydrogen colors. If the hydrogen is produced and comes from carbon, like natural gas, petroleum, it will generate CO2 and CO. If hydrogen generates by electrolysis, we need just electricity to generate hydrogen and oxygen. And if we use electrolysis plus renewable energies, we got the green hydrogen. And we have to notice the next. Electrolysis process loses efficiency between 20 to 30% of the energy. There are other ways to produce hydrogen, like bioethanol, having hydrogen and acetaldehyde here in Ecuador. And also, we can try a thing on a nuclear to produce energy and hydroelectricity too. What about South America and Ecuador? The feasible technology to implement in Ecuador. Biomass is switchable to produce bioethanol. Hydroelectric is another way. The country has 27 hydroelectrical plants. However, approximate waste of 50% is a sum. Apply hydrogen economy in the country, overcome the barriers. First, low and dispersant investigation activity. Second, low academic formation needed to operate and innovate on hydrogen technologies. Third, the lack of legal framework and regulations. And finally, the incipient formation of collaborative networks in research and promotion. What are the materials and methods? Okay, we use literature, we use an hydrogen vehicle simulation framework to here in Ecuador to know what it could be. Then the simulator was configured for fuel economy tests, aggressive drive, cold drive, and hot drive. And with those results, we apply principal component analysis, that is a technique of dimensional reduction, use sophisticated underlying mathematics principles. Also, with Excel and mini tabs, we can organize data to do maths and statistics about the research paper. So what are the results? In 2016, Argentina, Brazil, and Venezuela cover 76% of the commercial hydrogen production plants in South America. And Ecuador does not appear on the list due to the various percent. To achieve an hydrogen economy in Ecuador, it's important to produce it a massive, clean, and safe and efficient way. An alternative is implementing a nuclear hydrogen plant, a very high temperature reactor, for example. So if we use that, we can know the alternative is a helium gas cooled graphene moderate thermal neutron spectrum reactor that can provide electricity and process heat for a wide range of applications, including hydrogen productions. Those are our reference, then require a deeper study. However, the cost of production of 1 kilogram of hydrogen would be approximately in $2.15. So while I was doing this presentation, I saw that the new that sees green hydrogen cost coming down to $1 per kilogram in 10 years. So we can do it. Also, the different producers and their capacity, we can see in South America, Hyundai Wilson is the best company to do it. However, we got since 2015 a decrease of the production for captive hydrogen on the different refineries. So vehicles operating in US and Ecuador, for example, Toyota Mirai and Honda Clarity account for more than 80% of hydrogen vehicles in US. That's on March 31. So what I'm trying to say, even though there are hydrogen production plants in South America, observe those cars that use hydrogen on the street is not frequent. In South America, there are just 9 hydrogen demo cars or projects related. Hydrogen cars base cost in US is higher than best-selling cars in Ecuador, and we can see that in the presentation. So commercial hydrogen cars are not available here in Ecuador, and its price is 2.62 times higher than the average price of the best-selling vehicles in the country in 2020. Comparing Hyundai Nexo and Kia Sportage of both for 5 passengers, Nexo requires 1 kilogram per hydrogen to cover 100 kilometers. The kilo price at $12, we got the autonomy of 12 cents per kilometer. Taking the advantage of the green hydrogen project Catapult, the ratio drops to 2 cents per kilogram. That's in the future. And a comparison with Kia Sportage, the ratio is 5 cents per kilogram. We have to think on this. What is the hydrogen egg dilemma? And we present a special solution. What is first? Assemble the infrastructure to lower the price and promote consumption or consumption to accelerate the implementation of the infrastructure. Paris in 2015 it had 5 hydrogen taxis. In 2019, around 100, and 2026 units were expected. In 2018, 2,055 combustion taxis were registered in Ambato City. So, gasoline versus hydrogen taxi economy. The driver of a taxi has an income of $45 per day on 300 kilometers range. The cost of hydrogen with the green hydrogen catapult will generate $16 more than the use of the gas. So the amount of hydrogen required for the circulation of those taxis could be or will be 2.25 megakilograms. In that way, Tungurahua province, whose capital city is Ambato, has the potential for hydrogen production from photovoltaic energy, which is 1 year would be capable to produce 3.29 mega hydrogen kilograms. It is enough to cover the demand of the 2,000 taxis from Ambato City. Running the simulator of a principal component analysis, we can see that there are 10 variables involved. First principal component represents the 75.8% of the total variation. So what does those results mean? We have to pay attention on this. First, the amount of hydrogen before, while, and after a hydrogen vehicle function. Second, the calculated fuel economy and range, and then the route distance about the vehicles that we can use here in the country in future years. With it, we pass to the conclusions that we can say that Ecuador has a potential hydrogen production with biomass. It's another alternative, photovoltaic, solar energy, and maybe in future a nuclear plant. Toyota Mirai is the most accessed hydrogen car. Hydrogen vehicles are not available yet in Ecuador, and hydrogen cars are 62 times higher than the average price of the best-selling cars. Also, the ratio of Hyundai Nexo is 12 cents per kilometer versus 5 cents per kilometer of a Kia Sportage that use gas. However, with the green hydrogen catapult will be Nexo a ratio of 2 cents per kilometer. Also, Ambato taxi driver will have $16 of extra per day if he use hydrogen vehicle. So that's the presentation, and if you got questions, let me know, please.
Okay, Geoffrey, thank you very much. Folks, you can ask questions turning the microphones on and just asking, or you can use the chat function on Jitsi.
Okay.
Okay. If nobody have a question, I also have ones. Geoffrey, you said that there are 9 cars in South America, in the whole of South America.
Yes, there are
Where are
9
they?
cars registered on South America, like projects, demo cars running while just to do investigations, research, test, and not for commercial or not from people use. So that's incredible. However, we can implement more cars here or start to import those technology. However, those cars use hydrogen. In South America, we got plants to produce hydrogen. However, we cannot just buy like a gas station. So we should implement those kind of technology. And to implement those kind of technology, we can try to we got the source hydrogen. We have to produce it on a clean way. We got the demand, we got the cars, and also we have to join those aspects to implement those technologies here in South America.
Okay, I see your point. It's a very interesting approach, a very interesting idea to use hydrogen, but the cars themselves are very expensive. I'm from Brazil, and if I want to buy, for example, an electric car here, I'm going to pay a lot of money to get a basic car. So unless we have support from the governments, this kind of incentives, this is going to be very hard to make it work. But
yes, it's a very, very hard work that we can implement. I hope in 20, 30 years we can see hydrogen cars running on the streets of Ecuador. I hope being a mistake. However, it all can happen. Also, for example, here in Ecuador, have a Toyota car is like have a luxury car, like a BM, Mercedes, or those cars of those companies. And to reduce the cost, we have to educate the people to learn. They have to learn and know that we have to change our fuel from not to combustion. So we have to complement hydrogen combustion and then leave the gas.
I see. Well, thanks. Congratulations on your work. Do we have any other questions for Geoffrey? If not, Geoffrey, thank you very much. Good work. And I'm going to call again the other presenters for this session. That's the session GenTrack 5-9. Is Mr. Pornpimo present? I don't see, but I see Mr. Nikhil Kumar.
Yeah, I'm present.
Hi.
Hello.
Hello. Can we go ahead with your presentation? Can you share your screen with us?
Yes, of course. I'll present. Just a second. Tell me when it's visible, please.
Mr. Kumar is going to present a paper titled A Threefold Machine Learning Approach for Detection of COVID-19 from Audio Data.
Yeah. Is it visible now?
Okay. Please go ahead.
Okay. Yeah, so hello everyone. I'm Nikhil Kumar and I'm a student at BITS Planning from India. So my team and I, Vishal Mittal and Dr. Yashwardhan Sharma, we worked on, as the title says, machine learning models to predict COVID-19 from audio data, basically a binary classification task. So first, a quick overview of what I'll cover over the next 10 or so minutes. So a background, an introduction to the problem, followed by a description of the basic machine learning pipeline, namely data collection, data processing, and then training and evaluation of the models. And finally, what conclusions we can draw from the results. So first, about the background and the approach. So given that we have audio samples of breathing and coughing of individuals, can we partition the group into individuals without COVID, also known as the normal class, and individuals with COVID? So currently, the research into automated COVID diagnosis has mainly had two approaches. So using chest X-rays or CT scans, and the second is thermal images. So the problem is they both require specialized equipment, and the process of getting an X-ray is not non-invasive and involves contact with others. Also, thermal images are not necessarily indicative of COVID. It could just be a mild fever leading to a high false positive rates. So the approach using audio samples offers a use case where individuals can upload audio samples with just their mobile phones with no special equipment that is required, and can be done in an as contactless manner as possible, so that reduces potential exposure. So usage of audio samples for this task has generated a lot of interest in the recent years. So for example, the COVID-19 sounds project at the University of Cambridge, which aims to perform a similar binary classification, and the Koswara project at the Indian Institute of Science, which is building a data set for the same. So when we think of audio, when we thought of audio samples, we had three levels of processing that came to mind. So first is highly processed or highly metabolized, where we extract a variety of features and pass it to a model, basically completely spoon feeding it. The second is medium to highly processed. Again, here we extract features from the audio sequence, but we do it over short units of the audio. Thus, the input to the model still has some semblance of a sequence. And the last is minimally processed or minimally metabolized, which passes a visual representation of the sound as a spectrogram, and we do not perform any feature extraction. So it turns out that these three approaches or these three levels of metabolization have a direct correlation with the kind of model that we will be using. So highly metabolized, we have a table of features that we get, and this would be in the form of a structured table. And turns out that traditional machine learning models do well with structured data. The second, with medium and highly metabolized data, has a sequence as an input, and recurrent neural networks do well with sequences. And lastly, with the spectrograms approach, which is an image, convolutional neural networks have shown to perform well on image data. So for the data collection, we reached out to the University of Cambridge, the same COVID-19 sounds project that I mentioned earlier, and licensed their data set. So they collected the data set. Basically, they crowdsourced the data set from two sources. One was from an Android application, another from a web application, and put it as a data dump. We cleaned that up, and we have breath and cough samples, around 1,130 samples for each breath and cough type, and they had they had classified it as asthma, COVID, and normal. However, for our use case, for our purpose, where we want to perform a binary classification of COVID versus normal, we discarded the asthma samples and just used the COVID and normal samples. As you can see, the number of samples is very imbalanced, in the sense that there are around 172 samples of COVID and 795 normal samples, and similarly for the cough data. So that is one of the concerns or the issues that come in training the model as well. So for the pre-processing, the audio samples are all of different lengths, but both the CNN, that is the convolutional network, as well as the recurrent neural network need audio samples of the same length. So we choose a threshold length and bring all of the audio samples to that threshold length. So if the audio sample is shorter than the threshold, we loop it back. So for example, if our original audio sample is the blue sample here, and we want to bring it to say 1.5 seconds long, then we just loop it back until it reaches that length. And and if it's longer, then we just clip it to the length that is required. So how did we decide the threshold length for which we want to bring all the audio samples to the same length? So as you can see, these are the histograms of the audio lengths. So all the way from, for the breath samples, we have audio samples all the way from 1 second to 3 seconds until 35 seconds. And for cough, we have around, again, 3 seconds to around approximately 18 to 19 seconds of audio length. So we chose the 95th percentile of audio length because that seemed reasonably a good trade-off between how much information is lost in clipping the audio set and the amount of processing time that it takes. So for the breath samples, we brought all of the audio samples to the length of approximately 24 seconds. And for cough, we brought them all down to 10 seconds. Now coming to how we generated the spectrogram, first a short introduction into how a background into digital signal processing, a theorem called the Nyquist-Shannon theorem. So suppose there is an audio signal in the form of this green sine wave, and it has a maximum frequency f max. Then you would need to sample at least twice that maximum frequency in order to avoid aliasing effects. So aliasing is basically what happens when you say you sample the audio signal at these blue points. Then instead of tracing out the green shape, you trace out the red shape, and you get a totally different audio signal. So we don't want that to happen. And on performing our exploratory data analysis, we found that the magnitudes of frequencies greater than 8 kilohertz were negligible. So even if we lost that data, it would not be a big amount of loss of information. So we sampled at twice 8 kilohertz, which is 16 kilohertz. Now, so why spectrograms? So spectrograms, one, obviously because you generate an image which you pass into a convolutional network. Second is that if you have a raw waveform, you have no frequency information directly available. And suppose you take the Fourier transform of that audio signal, you lose all of the temporal information. So to make the best of both worlds, we use a technique called a short time Fourier transform, where you partition the audio signal into short chunks and take the Fourier transform of those chunks. And those chunks may overlap with each other. And you plot the spectrum for each of those chunks or each of those time units. So basically in this would be an example of a spectrogram where you have time on the x-axis. So these are all the chunks that we took. And for each chunk, we plot the frequency as the color, as the amount of color that is present. So a high yellow would be a high magnitude of that frequency. So, and since the FFT assumes that there are non-zero, that there are zero values at the edges, to make them zero, we use something called a hand window. And another concern was without scaling, all these frequencies are actually scaled by a log factor. So without doing that, your frequencies are not visible. So we perform a log scaling of the frequencies. And to make it more authentic, to how humans perceive it, we use something called a MEL scale, which is a variation of log scaling. It has more extra factors. Okay, now the types of features that we extracted for the machine learning model. So there were 3 types. One is instantaneous. So we, again, similar to the short-term Fourier transform, we again partition the audio sample into different lengths, and you extract the features over those short lengths. So in essence, you get a sequence of features. The second is global features, where you calculate the feature across the whole audio signal. So for each audio sample, you get one value. And the third is aggregate instantaneous, or AI, where with the instantaneous features sequence that you get, you perform some sort of aggregation, like taking their median or their mean or some other aggregate function to get a single value. So what do we use where? So the traditional machine learning model can't handle sequences. So we pass single values, that is the aggregate instantaneous or the instantaneous values. Aggregate instantaneous or the global values. And for recurrent, since it can handle sequences, we pass instantaneous features. So in a sense, each input is a sequence. Now the actual features that we used were six features. One is called RMS energy, which is root mean square energy, which tells us how much energy is there in the signal. The second is zero crossing rate, which gives an idea of how noisy the signal is. So basically, it is the number of times that the signal crosses the x-axis. The third is spectral centroid, which is a frequency or a spectral feature, and it gives you an idea about what frequencies about what value your frequencies are distributed. So basically, like a center of mass or a center of frequency. The fourth is spectral bandwidth, which gives you an idea of how varied the frequencies are, the spread of frequencies basically. The fifth is spectral roll-off, which is the frequency below which you have p% of the energy value. So in our case, we used p is equal to 85. Commonly used values are 85 and 95. And the last is actually a set of 13 features, so MFCCs. So they're called Mel frequency cepstral coefficients. So basically, I don't know if there's a direct analog to or a physical analog of what this means, but it's a commonly used audio signal processing feature. So it is, you take the discrete cosine transform of the Mel spectrogram. So it's essentially like a spectrum of a spectrum. Now, coming to the results and the training of the ML model. So we use 6 features along with 18 aggregation functions. So in total, we got 6 into 18, so 108 features, which is a lot. So you have a very wide data set for few number of samples. So to reduce the feature size or the feature dimensionality, we used PCA and reduced the feature set to 20, after which we used a support vector machine and performed 10-fold cross-validation and performed grid search to find out the best values of the hyperparameters, such as the L2 regularization term or the parameter for the kernel. We used a radial basis function kernel, and this actually performed the best among all the 3. And I think this can be attributed to the fact that we passed the most metabolized data to the ML model. So these were the confusion matrices that we got. This was for the breadth data, and this was for the cough data. As you can see, these are reasonable results, where we got around 0.935 precision and 0.828 recall. And similarly with cough data, we got 0.895 and 0.971 recall. So these are the best that we got, but it's coming to the next one, which was the convolutional model. This, in fact, performed very poorly, in which it was incentivized to predict all of the values as normal. So it's a completely useless metric, even though the accuracy is high because there are more normal samples than COVID samples. It does not do well on the metrics that actually matter, which are precision and recall. So to resolve this, we tried giving a higher weight to the minority class. That is, there were few samples of COVID, so that would be the minority class. And the other approach that we tried was undersampling the majority class or the normal samples. And lastly, we also tried artificially augmenting the MEL spectrograms. So what we did was, suppose this is the MEL spectrogram that we have. We shifted it up to 0.2 times in the width. So basically, we shifted it forwards and backwards in time. So that and this is a meaningful transformation because the signal is, it does not matter where, at which point in time it happens. So for instance, you can't perform rotation transformations because then you lose the semantics, because these would no longer mean frequency and time axes or other normal techniques that you follow for augmenting in computer vision tasks like zooming or cropping. And then we use the Adam optimizer with an initial learning rate of 10⁻⁻⁴, and on each time the validation loss plateaued, we reduced it by a factor of 0.05. And the poor performance can be attributed to the MEL spectrograms. If we looked at all the MEL spectrograms that we generated, they were all very similar to the naked eye. So it would be unfair almost to expect the model to discern. One can argue that the model might learn to discern it, but it did not do that, in fact. And the second would be the large class imbalance that was present. So we had many more normal samples as compared to COVID samples, as shown in the introduction slide. And this was the architecture that we used. So a general architecture with convolution followed by max pooling layers until you flatten it, and then you have a fully connected layer. So, and lastly, coming to the recurrent model, again, like the convolutional neural network, this was highly sensitive to the imbalance, and we tried downsampling it, downsampling the majority class, and the performance did improve, but the performance was still very pale compared to the traditional ML model or the support vector machine. So even on the training and test metrics were around the same range of 0.6 to 0.75 for breath and cough, and recall metrics, both training and test, were around the same range of 0.67 and 0.83. So the principal cause for this would likely be that the model is underfitting, so you don't have good metrics on the training data itself. So we could solve this by having by introducing more data. And if you recall, we had only around 1,000 samples, which is quite a tiny data set. Now, what can we take away from this study? So the first thing is that the traditional ML model works well with highly metabolized data as expected. So if you see, the more metabolized the data is, the better the performance is, even though you're comparing across different types of models. The general performance improves the more spoon feed you, the more you spoon feed the model. So ML model had more metabolization compared to recurrent and the convolutional ones, and they performed in a similar order. And the failure of the convolutional model we can attribute to because we manually extracted. We didn't manually extract too many features. We just converted it into a spectrogram and passed it as a raw input. The second was the MEL spectrograms did not differ from each other very drastically in order for the network to learn to discern them. And the last possible reason would be that there is a high class imbalance. The recurrent model seems to fail primarily because of the high class imbalance, and that can be solved with adding more data. And as in any machine learning task, there is no data which is not enough. So all the more data is helpful. So this is what we can take away from this study. This brings me to the end of my presentation. So if you have any questions, I can take them.
Okay. Thank you, Mr. Kumar. If you have any questions, you can either talk on the microphone, turn on the microphone, or you can type on the chat. And actually, I have one question. This is a very interesting approach. It's too bad that we don't have much more data about that. It looks like it's only a few labeled examples. But one question that I have is, do we have the data that you use it? Do you have any additional information on the data, for example, sex, age, location, or just the sounds?
Just the sounds. It was all anonymized before we were.
Okay, it's interesting because I recall to read in some place that factors like age and other factors that can impact on this kind of sound recognition. But nonetheless, very interesting. You've got some interesting results with a few data and not all the interesting data we can have. That could be very interesting if you could develop an application to do that, but it's going to be a lot of work. So, folks, do we have any other questions for Mr. Kumar? Okay, if we don't have any other questions, I'd like to thank you again, thank all the presenters, and call again Mr. Pornpimo Chayutisak. If you're present and you would like to present your paper, Mr. Pornpino. No, I don't see him on the list of presenters. So, on behalf of the ICCSA Organization Committee, I'd like to thank you very much for your presentations and invite you to enjoy the rest of the conference. There are several different parallel sessions and some keynotes that are still going to be held tomorrow. So thank you very much. And with this, I close this session. That session was GenTrack 5-9. We can meet again in session GenTrack 5-10. That's going to be on the same virtual room C at in sort of 22 minutes. Okay, folks, thank you very much.
Thank you. Bye-bye.
Okay.
Thank you very much.
Rafael, the room is yours.
I'm here. Mr. Santos, can I remind you to fill the evaluation form for the paper?
I have the form here. I haven't filled that yet.
Okay.
I have my notes. I'm going to do that.
Okay, thank you very much.
Okay.
And we can take a break then and come back at half past 16 for the next session.
Okay, 16:30. Thank you very much.
Thank you.
is on.
Raffaele, are you there?
Yes.
Okay, I think we can start.
Yeah.
Okay. Okay, folks, good afternoon in Italian time, it's still morning in Brazil, and welcome to ICCSA General Track 5-10. My name is Rafael Santos, I'm with the Brazilian National Institute for Space Research, and I'm going to be the chair of the session. We have 4 presentations programmed for this session. The first one is Franklin Barbosa and Renato Ishii, a neural network approach to high-cost patients detection. Franklin or Renato?
Hi guys, good afternoon.
Hello, Renato.
Nice to
So
meet you.
can you go ahead and show us the presentation?
Okay, can you see that?
Yes, we can see it. A reminder, we have 10 minutes, you can pass a little bit but we have also 5 minutes for question per presentation. So please go ahead. Thank you very much.
Okay, thank you, Rafael. Good afternoon, guys. My name is Renato Ishii. I will present the paper entitled Neural Network Approach to High-Cost Patients Detection. This presentation is about healthcare. Healthcare is one of the largest components of the global economy. According to World Bank in 2014, healthcare expenditures accounted for 9.95% of the world total gross domestic product. Additionally, per capita health expenditure have increased during the last decades. Effective management of human resources will allow health systems to respond in timely manner, improving healthcare outcomes, rationalize the use of resources, and reduce the stress on staff. And the COVID-19 pandemic further increased these needs. High needs, high cost, abbreviates HA and HC patients are variously defined in the literature as a small subset of population who account for the majority of healthcare costs. Lack of consensus of the defining attributes of HA and HC patients has challenged the effectiveness of interventions aimed to improve disease management and reduce costs. Like, for example, in 2013, 5% of Medicaid aids, highest cost beneficiaries in United States, account for 54% of total expenses. So the main problem with the way product records work is detection, the high cost patients. And therefore a valid, reliable, and implementable approach to accurately predict HA and HC patients is critically important for designing targeted intervention that can effectively lower healthcare spending. And a viable approach is, in this scenario, to detect patients who are at risk at becoming high cost before these transitions take place. So HA and HC cost patients defined who's accounting top 5% of annual healthcare costs was as much as half of the total healthcare costs. And machine learning models can assist healthcare management to decision makers. And accurately predict future HA and HC patients and designing target interventions for them has the potential to effectively control rapidly growing healthcare expenditures. Our objectives in this work and to achieve this goal is to implementation of neural network models to describe that problem and compare the results obtained in our work with those found in previous works, basically works defined of China's 2012, and development the needs of all tools and a toolkit to create the proposed models and validates of attributed sets defined by China's 2012. Our methodology summary have 4 steps. 1 and 2 steps are the pre-processing step that consists of a set of techniques and activities on the chosen datasets. Our dataset we choosing is a MAPS, Medical Expenditure Panel Survey, is a data set of large-scale surveys of families and individuals, their medical providers and employers across the United States. For the purpose of this work, we consider the process defined by TINAS 2012. More specifically, only individuals older than 17 years were considered. In total, 39 attributes were chosen, divided in 5 categories: demographies, health status, preventing care, priority conditions, and visits counts. The data sets have 11 years from 2006 to 2016 of data, resulted in 125,457 total records. We have considered the top 5% of the population as high cost. As such, the data set can be divided into high costs containing 6,000 records. During training, the resulted dataset is divided randomly between training and validation datasets, where the training sets contains 80% of the records, while the validation dataset contains the remaining 20% of data. The next step of methodology is modeling, which involves analysis and the construction of models that best fit to the problem. For this purpose, we use Keras together with TensorFlow to model such problem. The next step of methodology is the benchmark process, which consisting of evaluating the results obtained by the models generated by previous phase. For the benchmark process, initially metric related to the success rate of the algorithm will be considered, such as accuracy, precision, recall, and the metrics generated from them. The last step is the result analysis. The resulting model is formed by 3 hiding layers with 32, 64, and 32 nodes, respectively, with dropouts applied to every layer, with elimination rate of 0.5. Function used in the layers, in the hiding layers, was rectified the linear unity rule and hyperbolic tangent function for the output layer. When we compile the model, the RME-SPROB algorithm was used as optimizer, and the last function used was cross entropy. Finally, the model was trained for 100 epochs with a batch size of 32. Every model was trained separately 100 times, each using different low-cost records. The results were for each network were logged, and the average results for each metric was calculated using the results found in each iteration. This process was done twice, once using the sum year expenditure. In this slide, we consider first year values as a parameter to define high cost individuals, and then using second year or second year values. For the sum year prediction, the metric for the best perform model as detailed in this table, and we consider sensitivity, specificity, accuracy, precision, and F-score, and the standard deviation. In the next table, we consider the second year. All results are similar to the ones obtained by neural networks constructed by Chines 2012 and Sun methodology, accepted by accuracy. Chines considering two decision tree techniques and neural networks. This corroborates the minimal set of attributes defined in that work, in addition to suggesting that similar or better results can be achieved with a greater quantity of data and more recent data. Another point of view, we consider a comparison with Meehan 2015, shown in this table, who used traditional machine learning algorithms to generate models for the same problem, HN8C patient detection. So our results are similar to proposed previous work. This corroborates with the minimal attributes set defined in that work. While the metrics presented are similar, we detect the false positive in schemas are higher as compared with our approach. This also suggests that similar or better results can be achieved when more data is available, if we consider a big data age, for example, and we imagine that the data is very available in the future. Our main contribution is the validate the prevalence defined attributes. We concluded that neural networks are a valid approach to deal with such problem. And as more data becomes available in the future, both from the MAPS dataset or another dataset, the results can be improved. We create of necessary tools, a toolkit available on GitHub repository to deal with maps files in a very, very single way. We would like to thank our Brazilian institution, Intercity Project, and our laboratory. And thanks so much for your attention, and I open for questions.
Thank you, Renato, for the presentation. Folks, you can either ask questions directly turning on your microphone, or you can use the chat if you have questions. And as often I have one. Actually, I have two questions, Renato. Just to be sure, I heard that the data that you're using, you're considering only patients that are 70 years old and older. 70.
Yes, 70.
Is that any reason why you couldn't apply the same methodology, for example, for ICU, neonatal ICUs, or different ranges? Or right now we are suffering with COVID, so we have a lot of patients that are not on this. Is there any reason for that, just out of curiosity?
Oh no, this reason is based to compare of previous work, only this situation. We think you use data source. you can the data source, but data source is very, very complex to extract data, and for reasons of to compare previous work, we consider maps dataset. But our methodology can apply for another data sets, and we think in the future consider data source.
Okay. You are with Federal University of Mato Grosso do Sul in Brazil. Which department?
Faculty of Computing.
Okay. Okay. Just to be sure that some people in there are some people there in public health, so you're just in the computer science.
Oh, very nice.
Okay. Okay, Renato, thank you very much for your presentation and congratulations on your work. If we have any more questions, we can ask here, or we can go for the next presentation. That's João Cunha. João Cunha is there, and João Cunha, Pedro Diniz Gaspar, Eduardo Assunção, and Ricardo Mesquita are going to present a prediction of the vigor and health of the pitch tree of CAD by processing and analysis of UAV-based multispectral images. João, are you ready to start the presentation?
Yes, of course. Good afternoon, everyone.
Okay.
I hope you can see me and
yes,
and hear me well. So, can you see the presentation?
We can see it. Please go ahead.
Okay, thank you. Good afternoon, everyone. My name is João Cunha, and I carry out this study with the help of Professor Pedro Gaspar, Eduardo Assunção, and Ricardo Mesquita. Modern agriculture is increasingly dependent on systems based on new technologies, which involve robotics, image processing, remote monitoring, and even artificial intelligence in the development of methods of support decision making. Remote sensing systems can be used to identify and map a variety of phenomena, including small to large variations in characteristics, health, and condition of vegetation across the landscape. Vegetation conditions is a measure of vegetation response to stress. Good condition is associated with green. Plants respond to the stress by reducing chlorophyll activity and subsequently producing other pigments, as we see in this image. Vegetation index is generated by combination of 2 or 3 spectral bands, whose values are summed, divided, or multiplied to produce a single value or index that can be used as an indication of amount of vigor of vegetation. To calculate vegetation index, it's necessary to delineate the area of interest, or canopy areas, which can be supported by a computer vision method. In this job, we use artificial intelligence method of image segmentation called faster region-based convolution neural network. The images were captured by MikaSense Red Edge MX multispectral camera attached to a drone. This camera simultaneously captures 5 discrete spectral bands, such as blue, green, red, red edge, and near infrared. In general, these 5 bands were used to generate accurate and quantitative information of cultures. The images were captured in the peach orchards located in Quinta Nova, Torresendo in Portugal. For this study, we use 20 multispectral images, and in each image there is approximately 16 tree pitch canopy. Therefore, the database includes a total of approximately 323 canopy. The 5 image channels are spatially misaligned due to the physical distance between each sensor. This phenomenon is known as parallax. To resolve this issue, the camera manufacturer provides an alignment software. Each vegetation index is a number generated by some combination of remote sensors and with a relation to amount of vegetation in each image pixel. Normalized difference vegetation index is probably the most commonly used index. Has values range from +1 to -1. Is calculated by a difference between near infrared and red reflectance and divided by the sum of the two reflectances, as shown in this equation. Increasing positive NDVI values indicate an increase in green vegetation. Conversely, NDVI values near zero and decreasing negative values indicate non-vegetated features, such as buried surfaces, water, snow, ice, and clouds. In this study, the faster region-based convolutional neural network model was used to detect the tree canopy. This model is based on a convolutional neural network which learns how to automatically extract the necessary characteristics of a digital image to solve a computation vision task. The proposed method for checking the vitality of a tree to evaluate the various vegetation indexes of a region there is a tree canopy is located in a digital image, since the vegetation indexes may reflect the health of a tree. In this study shows a base method on convolutional neural network for the detection of a tree canopies, as well the application of vegetation indexes to evaluate the vegetation condition of a tree in the peach orchard. This image shows the visual results obtained in the test image from Quinta Nova orchard. The rectangles represent the tree made in the faster region-based convolutional neural network model, and the ellipses are the regions of interest obtained from the rectangles found, in which the vegetation indexes corresponding to each tree are obtained. The table 1 shows the results of NDV vegetation index analysis of each tree and tree image. And the table 2 shows the results of 4 vegetation index, whose values are normalized to that direct comparison between results can be performed. The values of green normalized difference vegetation index and the normalized difference red edge index and the red edge green normalized difference vegetation index confirm that analysis previously done with NDVI index, where the trees 2 and 12 shown to be healthier, contrary to the 3. Their values of lower vegetation index were verified. This work was applied a method based on a convolutional neural network for the detection of canopy trees, as well the application of vegetation index to infer the vegetation conditions of a fruit tree in peach orchard. The values of the GNDVI and the RE and RE-GNDVI indexes shown that trees are distinguished by vigor levels. This work is relevant to support decision-making in agricultural activities, making it possible to optimize resources, reduce time and cost, and maximize the productions. So that's it. And if you have any questions, just do it.
Okay, thank you, João. As well, if anybody wants to do a direct question, you just turn the microphone and start talking, or you can use the chat. And if nobody have a question, I have 3 questions here. This is very interesting. The first question, this is not a technical question, it's just out of curiosity. Can you show the sensor again, the infrared sensor?
Can you repeat, please?
The sensor, the camera.
Yes. I don't know if you can see the mouse.
Yes, this is very interesting. I didn't know that. It's okay. Do you know, out of curiosity, how much is that camera?
The cost.
The price.
The price is very high. I think it's like 3 million. No, like 13,000 probably. I don't know.
Wow.
But
Okay.
it's very high because like normal cameras just have the blue, green, and red sensors, and this one have two more: the red edge and the near infrared.
Okay. Another question that I have is that you use that to analyze images of pitch occurs. And probably you can use the same idea, the same technology for different kinds of trees, like probably apples and oranges that are similar. But what
of course.
Do you think it's possible to use for very different kind of vegetation, for example, coffee? Because the NDVI doesn't work very well with trees that are sparse. They have a lot of long branches and a few leaves. I'm not sure NDVI is good for that. Do you think it's possible to use it?
This one is just a test. This is just a test in this type of trees. But in other type of trees, I don't know. We can try it. We can try it like, but I don't know if he is successful.
Okay. If that wasn't very expensive, I would like to try it with Brazilian plantations of coffee. But it's 30,000 euros. It's quite a lot of money.
Yeah, of course.
Okay, João. Thank you very much. Do we have further questions for João? So if you don't have, I'd like to thank you again, João, for the presentation. Congratulations on your work. And I'd like to call the next presenter. The next one is going to be James Deng or Clement Leung and Kristen Lee. Are they present? We have a fellow Jitzer. So Mr. Deng, Mr. Leung, and Ms. Lee, they are not present. What about Rafael Razieira and Dilberto Rodello? Are they online? Okay, it seems that there are just the four of us. We still have time. So what I'm going to do is, Rafael.
I can think we can finish now the session because there is no other presenter.
Okay. Okay then. So thank you very much. Thank for the people that presented. And we see you again in the next sessions. Please enjoy the rest of the conference. Thank you very much.
Thank you so much, Rafael.
Thank you.
Thank you.
See you around.
Good afternoon, everybody. Ladies and gentlemen, my name is James Romby. I will be the chairman for this session. Can you see me? Can you hear me?
Yes, we can.
Okay. We will start in a few minutes, okay?
Volete leggere della chat? Nel caso qualcuno scrive.
I just remind you that you've got 10 minutes for the presentation and then 5 minutes eventually for questions. Also, you can ask the questions using the microphone. If not, you can use the chat to write and answer any questions. I think we can start. So the time has come. So the title of the first presentation is COVID-19, Impact on Higher Education Institutions, Social Media, Content Strategy. I would like to introduce, I guess the presentation will be done by Tiago Coelho. Are you connected? Can I have any information about this presentation? Conosce il microfono, aspetta.
Tutti i microfoni spenti.
Ok.
Ecco, un secondo.
Ah, ok. Mi ha scritto che pure deve avere il permesso per...
Teoria no. No. Un problema solo.
No, I think, Tiago, you can start. There's no permission by this side. I think you can just click on your microphone and we can be able to hear you. Vero, cioè... Ah, è collegato, sì.
Non so se forse è una connessione molto scadente. Adesso mi stai provando.
We're just waiting a few seconds to see if Tiago can manage to connect again. Tiago, hello? Yes? No, we can't hear you. Your microphone is still on off. Also the microphone and the camera.
Tiago, can you please check if in the settings screen of Jitsi you have the right microphone, right camera selected, please?
Disconnected. We can see that you are connected now. Okay, and we'll do this then, Thiago. We will go with the next presentation and then we'll come back to you, okay? So you can manage to fix and verify what's not working properly. Okay?
Yes. Well, if you can try to use Chrome as a browser, because other browser can give problem with Jitsi.
Did you hear that, Thiago? Okay, he's using Chrome. Okay. We will be back to you later, okay? So we can carry on. We can go to the second presentation of this session. There are a total 4 presentations. The title is Data Science Mentoring Support Using Neural Networks. Please, you can start the presentation.
Okay. Are you hearing me? Are you hearing me?
Yes, we can hear something, but it's not very clear. Maybe the microphone. You need to go much nearer to the microphone. Okay. And also, we can't hear you. I'm sorry, we can't see you.
Right.
Now, okay.
Can you hear me?
Yes, video is on.
Okay. So I'm going to present this. Are you watching?
Okay, we can see the presentation. Fine.
Okay, fine.
You can put it full screen, okay?
Okay. So I will start. Good afternoon, everyone. I am Michael Campos.
The volume is a bit too low. Maybe you need to go much more near to your microphone.
Okay. Well, let me see. Hello?
Yes.
Hello, here.
Oh, it's better now.
Good afternoon, everyone. I am Michael Campos, and this is the presentation of the project called Data Science Mentoring Support Using Neural Networks. It was developed in the ICCSA lab at Fourier by Michael Campos, Felipe Borges, Araujo, and So let's start by mentioning our motivation. Put in context, our lab is focused in the area of science. After the pandemic, the number of students increased considerably. This also led to a higher demand for online assistance from teachers, as they have to dedicate more time to this task. This led us to look for a solution that allows automatic attendance. This is when we search for natural language applications, which have shown great advances in recent years, based on architectures such as the so-called transformers networks. Then our proposed solution consists in the implementation of a chatbot to reduce the workload of our teachers. This chatbot has two main features: automatic answers to frequently asked questions, such as concepts, among others. And the second one, generate questions that allow to evaluate the student and also that they can self-evaluate themselves.
Is it the first slide or the second slide? Sorry, because here it's on the first slide still. Okay.
Sir. Now, let's see. Now,
Yes, okay. Could you put it full screen? Okay, now it's full screen. Okay.
So, well, I will continue. In order to better understand the development of the project, let's define some main concepts. First, information retrieval. Its best known example is the Google search engine, in which we enter a text to search, which we will call query, and it shows you different web pages, sorting order of proximity to the query. The difference with our project is that this process will return the closest text inside our database. The next one is the semantic textual similarity, which evaluates how semantically similar are two texts. They could be paragraphs, sentences, or even words. The third one, neural question answering, as its name says, consists of answering questions. Now, this can have two types of inputs. The first only requires a question, while the second requires the question and the text that contains the answer. The last one is known also as reading comprehension. And finally, neural question generation. Unlike the previous one, this task generates questions from a text. Some of these networks also generate their respective answers. The last two tasks have in common the term neural, since they are based on neural networks. So this is the workflow, starting here, where the user has to specify the topic she wants to address. Then a menu is displayed with two options, question and validation, which follow the green and orange lines, respectively. Both go through the information retrieval model, with the difference that the green flow concatenates the topic with the question entered by the student. This information retrieval model searches our database for the context most related to the query entered. For this model, we use the RM3 model, which is an optimized version of the well-known VM25. These contexts enter to their respective main models that will be detailed later. But first, we are going to explain a little bit about how our database was built. For this, we use a software developed by our laboratory, which allows us to extract text from books. It was called Tornado. For our case, we search for free books in data science field. And feedback from our teachers, most of the students' questions are definitions. So we also extracted concepts from glossaries found on the web, for example, about machine learning and business intelligence, as well as from Python libraries like Pandas and scikit-learn. Now we come to one of our main models. This continues our green flow, where we have our inputs, the question, the context selected by the information retrieval model, and the database. In the first instance, as we mentioned, most of the questions are definitions. So we train a model to identify whether or not it is a definition. If it is, it will look for the most semantically similar definition from our database. In case it is not a definition, it will enter together with the context into a BERT model, which is a transformer network that was pre-trained with a database for question answering. In addition to the answer, this model provides a score of how good it considers the answer. If this is greater than an empirically defined threshold, we will accept it as the answer. Otherwise, it will pass to the generative GPT-2 model. We'd leave it for the end, since in many cases it has achieved accurate answers to open questions. To go into more detail, our intent classifier model was trained with an online database that had 150 different classes. However, we made it binary classification since we only care about whether or not it was a definition. For the representation of the questions, we use sentence embedding, which is a version of word embedding, but for sentences. But for this, we use the SBERT model. After having this representation, we train a basic logistic regression. Continuing with the question answering models, we have the structured one obtained from the library Hugging Face, which extracts the answer from the context. And the generative model, GPT-2, as its predecessor, GPT-3, has shown great results. Continuing with the question generation model, to generate question, the model requires us to enter candidate answers. Therefore, we use a keyword extractor, After the question are generated, they will go through the previous model, the question answering model, to generate more accurate answers, which are not shown to the user. This is because the chatbot also prompts the student to enter her answer, and it compares them using the semantic textual text similarity, which gives us a score of how close it is to the correct answer. It also can be configured to generate until 5 questions as if it were a quiz. For the extraction of keywords, we use the post-tagging technique of the stencil library, from which we kept only those identified as pronouns and nouns. While to generate the question, we use both UniLM version 1 and Prefinet model. Both were state-of-the-art at its own time. After testing them, we perceived good results in both, so we left them to allow more variety of questions. So this is the demo, which was implemented in an interface developed by IBM. Here we show the process for question answering. In the first instance, it asks for the topic and gives us some options when we have put deep learning. Then we choose option 1 for question, and we also have to put the answer, the question, right? So here we are writing the question that is, what is deep learning? And this shows the answer. This chatbot resets automatically. So to evaluate the chatbot, we choose 2 different weights. The first one was based on metrics. As this is a mix of different tasks, we put them in a table with their respective database and metrics. This is known as automatic evaluation. For example, we can observe here our intent classifier, which reached a great accuracy. The second type of evaluation is a bit more relative, since we recorded 70 questions and with their respective answers, and asked 3 experts in the field to score them in values of 0 if the answer was not clear, 1 if it was almost right, and 2 if it was good. From this evaluation, we observe an average of almost 1, so we can say that it has accurate results. So, well, finally, to conclude, we can say that we are on the right way and that we can still improve the chatbot using neat techniques that are being developed in natural language processing. However, we must keep in mind that this also has limitations, such as the requirement of GPUs for greater fluency and speed of the chatbot. Thanks.
Many thanks for your presentation. Very interesting. Are there any questions? I don't see any questions, so thank you very much for your presentation. And we could carry on with the next presentation.
Can you hear me already?
Pardon?
Can you hear me already?
Yes, we can hear you.
Thank you. I was the one who's having the technical difficulties. Thank you for giving my.
You're back.
Yes.
Okay.
So should I start my screen share?
We can hear you loud and clear now.
Should I start my screen share then?
Yeah, okay. Okay, now we go back to the first presentation. The title is COVID-19 Impact on Higher Education Institutions, Social Media, Content Strategy. The floor is yours.
Thank you. So, as competitiveness and expectations increase and government funding decreases, higher education institutions need to find a way to ensure their subsistence. Many of them do so by joining social media platforms like Twitter in order to gain some sort of competitive advantage. The COVID-19 pandemic has led to many political, economical, and societal changes, and individuals have had to adapt, but also the organizations had to adapt. Therefore, in this paper, we study the impact of the COVID-19 pandemic in higher education institutions' Twitter content strategy, and we do so by first identifying 12 of the highest ranking institutions based on the CWR ranking, collecting their corresponding tweets for the study time period, the 2019-2020 academic year, And then, with the help of unsupervised machine learning methods, we identify the topic areas present in each hey content message. After that, we characterize the respective strategies and analyze the strategies obtained in periods before and after the COVID-19 pandemic. We started by exploratory data analysis, where we were able to determine some interesting characteristics in regards to the data set and the institution specifically. For example, if we observe the monthly average number of favorites and retweets for each hey, we can observe that the average number of favorites and retweets usually share the same behavior, one increasing and decreasing with another. Because of their high correlation. If we take the dashed vertical red line as the COVID-19 pandemic declaration date, March 20, we can see that the peak number of average favorites falls usually after the COVID-19 pandemic declaration, with only Chicago and Cambridge presenting as exception. Besides that, we were also able to determine that Harvard, Stanford, Oxford, and Berkeley shared the same event, characterized by two distinct peaks and two valleys, although not necessarily at the exact same time or with the exact same intensity. We also determined the institution's posting preferences by analyzing the following heat maps with weekday per hour. And we were able to determine that their activity was mostly restricted to a set number of hours, during which they concentrated most of it, and then we had the so-called dark periods with little to no activity. The weekends could be considered for most institutions, besides Harvard, dark periods with little to no publications as well. After this, we tried to identify the editorial model, and to do so, we utilized two different algorithms: the latent Dirichlet allocation, or LDA, and non-negative matrix factorization, NMF. We compared them both through an iterative process with an increasing number of topics. When we discovered the optimal number of topics for both of them, which happened to be 5, we then compared them in regards to topic coherence, topic interpretability, and intertopic distance, with LDA showing much better values for these metrics. So therefore, we proceeded with the LDA model. If we interpret the identified areas, we can see that the topic 0 seems to be related to events, because can be comproved by words like event, join, live, today, etc. Then topic 1 and topic 2 represent health or public health and research, respectively. Topic 3 can be identified as education, as can be comproved by words like learn, student, school, etc. And lastly, topic 4 was the hardest one to identify, and we use not only the 5 most relevant words from that topic, as can be presented by the following word clouds, but also least relevant terms. But lastly, we're able to determine that it refers to image, as can be confirmed by words like congratulation, world, good, work, but also words that are not present, like celebrate and history. After identifying the editorial model, we wanted to observe their strategic evolution over the study time period, and we got the following time series. We can easily observe in most of them the decrease of the research topic over the study time period and the increase of the health topic. If these characteristics are correlated, this could be because of the high semantic similarity between health and research. That between all the possible topic pairs were the ones that had the most semantic similarities. Besides that, we can also observe a sudden and massive increase in the number of health topics immediately after the COVID-19 pandemic declaration, and that is shared by all hey. Later, we analyzed the strategies by dividing the study period between pre- and post-COVID periods, and we got the following results. We can see that before the COVID-19 pandemic, we had Stanford, MIT, Imperial College, ETH Zurich, and Caltech, with the main focus on research. Then we had UCL, JHU, Harvard, and Cambridge, with focus on education. We had Berkeley and Chicago, with focus on events. And lastly, Oxford, the only institution with focus on image. The health topic was not focused by any of the studied organizations. After COVID-19, we can clearly see significant changes. Most of all, the the sudden takeover of the health topic. Institutions like Berkeley, Stanford, MIT, JHU, Imperial College, Harvard, and Cambridge, all of them changed their previous preference topic to the health topic. Only Oxford, Chicago, and ETH Zurich maintain the same topic, although with decreased levels of dominance due to the rise of the health topic. The institutions like UCL and Caltech showed the greatest changes by switching to a dominant topic that is not actually health. UCL changed to image and Caltech switched to events. After this, we wanted to see the impact of the COVID-19 publication directly in the areas and not the strategies. So we gathered the following histograms. And we can see that in regards to the number of retweets before and after COVID-19, events, health, and education had a significant increase, although research and image had a slight decrease. Besides that, despite that, research and image had a positive increase in the average number of favorites after the COVID-19 pandemic, making the overall number of favorites after the COVID-19 pandemic increase across all areas. If we observe the bottom bar chart with the number of publications before and after the COVID-19, we can see that research was the most prominent topic before the COVID-19 declaration, with close to 25% of all publications being about research. And then it's a further 11% decrease, making it the least common topic after the COVID-19 pandemic, and helped follow the inverse path, going from the least popular topic to the most popular topic, with close to 30% of all publications being about health. Education and image had a slight decrease in topic frequency, and events a slight increase. Based on the previous results, we were able to conclude that Twitter content strategies by higher education institutions seem to revolve around 5 key editorial areas: events, health, research, education, and image. In regards to those areas, we can see that health and research during the study period had opposing trends, one going from most represented topic to the least represented topic, and another going from the least represented topic to the most represented topic. This could be, as previously stated, by the high levels of semantic similarity, but also because of the current pandemic situation in which most of the research efforts are being placed within the health spectrum, mostly directed towards the COVID-19 pandemic. Besides that, based on the previous results, we can also determine that the strategies have shown to be affected by the COVID-19 pandemic. As you've seen before, there have been a lot of multiple dominant topic changes. Regards to events specifically, the events topic was the only one besides health that managed to increase in all of the 3 observed metrics, showing that a need for social interaction resulting by the current pandemic restrictions. The increase in health and decrease in research, in addition, we can also observe that COVID-19 pandemic had an overall positive impact on public interaction with the social media publications. This could possibly be because of an increased online presence of the public regarding the new COVID-19 pandemic restrictions, like homework and the homeschool. But also could be that the users are now more interested in the new content being published by those aides according to the new content strategy. Lastly, apart from the previous conclusions, our contribution in this paper is also in the form of a proposed general methodology for understanding and measuring social media content strategies in higher education institutions. And I will proceed to any questions you might have. Thank you for listening to me.
Very much. Thank you very much, Iago, for your presentation. Are there any questions? I remember you. There is one question that's been written on by a Figuera who asked, I believe self-promoting might be editorial line for higher education institutions, but do you believe images is a topic in itself or a combination of several other topics?
So this is actually a very interesting question. because with the further studies that we've been doing in regards to higher education institutions' content strategy identification, we were able to conclude that the image topic is not that well characterized. So image might be a composition of multiple topics, namely the topic employment, which is regarding the previous employment of the employment of previous alumni. Also, the topic faculty, which is related to the professors and the work staff of the college itself. And also society has a big impact on the image topic. What was perceived by this model as image, as self-promotion, can also be interpreted as social, as human rights, as social activism.
Okay, thank you very much. Are there any questions? I think that is it. Thank you very much, Diego, for your presentation. It was very interesting. Thank you very much.
Thank you.
Now we go to the third presentation. The title is Improvement of Optical Character Recognition for Structured Documents using Generative Adversarial Networks. The floor is yours. Okay, we can see the presentation, and now it's full screen. Okay, perfect. But we can't hear you at the moment. Is that Jose? We can see that you sharing your screen now. Okay, you're putting the volume of the microphone, but you got the microphone off on this, so you need to put that on.
Hello.
Okay, now we can hear you. Okay.
Oh,
now
sorry.
Okay, you're fine. And now we can see you. You can share your presentation now.
Oh, sure.
Thank you. Okay, perfect. Thank you very much. Okay. We can't hear you again. Jose, if you're there, let me know. Microphone. Ce l'ha acceso il microfono? Ok. USB audio device mono. Just check if is that the right microphone that you're using. Because we should see that it's not on yet. Okay. A default device, internal microphone build.
Audio output, microphone, cosa potrebbe mettere?
Okay, we'll refresh that. Can you try to refresh this page to refresh the Jitsi page?
Ok.
Perché a volte lo fa non aggancia il dispositivo.
Okay, you're connected.
Hello?
Okay.
Okay. Okay, let me share. Okay. So.
Okay, the magic of computers.
Okay. Well, my presentation is organized as follows. First, a brief introduction about the problematic, the methodology that we adopted in order to resolve the problem, and finally, the experiment and results that we performance in order to evaluate the performance of the proposed methodology. Okay. So our work is focused in the context of information extractions. One of the main challenges of enterprise search are to access to accurate and relevant information in all documents and technical reports and articles. Some studies estimate that 80% of enterprise information is unstructured data. So enterprise can now take advantage of the information that they really has in order to make decisions, and this is a problem. Many of these documents are scanned. That means that these documents are images. So extract information for these documents is more difficult. For industries with long life cycles, such energy and mining, all report could be especially important to make decisions. Enterprise can take information studies that have performed before and use this information to make decisions about new projects, for instance. So in the context of information extraction, the main idea is to use all documents that are available on the industry and process this information using a machine learning algorithm that organizes this information, put this information in a structured way so that the enterprise user can extract looking for information that are in the data sets. Let me first introduce the Tornado. The Tornado is a software that has been developed in our lab. Tornado is a software for information extraction. In the architecture of Tornado, it handles the data, the document, depending on the characteristic of this document. So for the case of text-based PDF, Tornado uses a PDF parser that convert this information, this information into a XML file. And for the case of the scanned PDF, Tornado use the Tesseract algorithm, using algorithm for OCR to convert the images into text, and then this text is also tagged into a XML file. So our work is focused in improving the performance of Tesseract algorithm, all OCR algorithm available. In the structure of the Tornado, it first detects all information present in documents. For instance, it detects the boxes corresponding to block of text, images for equation, and so on. So in the case of block of text, we have input this block of text, and we have the OCR algorithm that extracts the text present in this image and produce a digitalized version of this information, the text contained in that image. In this case, the Tornado used the Tesseract 4. Some limitations, like irregular background, for instance, not alignment text, noise, and of course, some kind of deformation in the scanning process make that this algorithm of OCR have poor performance in these conditions. Some solutions have been proposal that improve the performance of the OCR algorithm. Another one would be improve the image quality. In our work, we want to focus in the improvement on the quality of the image to also improve the performance of the OCR algorithm. In our pipeline of process, we have the inputs, the block of text. We first the text, the orientation of the text, and using in convolutional neural network for detection this orientation, we also rotate the image in order to guarantee the horizontal alignment of the text. Then we introduce a text cleaner net that it input that image and synthesize a new version of this image, trying to reduce the imperfections contained in this image. And with this operation, the other algorithm obtain better result because the characteristics of the character are better. So the objective of our work was to develop a system to reduce the anomalies on structured text to improve the OCR performance. The idea was to generate good quality image with homogeneous background, high contrast, horizontal alignment text, clear and without deformation. In our methodology, the text alignment test is basically a convolutional neural network that was trained in order to detect the orientation of the text. And the text cleaner net, in this case, we adopted a conditional generative adversarial networks. So in this conditional generative adversarial networks, the generator input text, image text with deformation, and it tries to synthesize a clean version of this image. Learn the mapping between dirty to clean image. In the context of training of the conditional GAN, the generator is trained, it input image with deformation, and it tries to synthesize a clean version of this image, so that it must be so realistic that the discriminator can distinguish between real and fake. Adversarially, the discriminator is trained to discern between pairs of fake real image and real images. In the experiment, we use the architecture based in convolutional neural network involved there. We use 9 residual blocks on the bottleneck, and for the discriminator, we use another convolutional neural network, a patch discriminator, but input image and produce a grid of a score indicating the realness of the image in different parts of these input images. For training, due to we don't have the per image in the real life, we generate synthetic data. So to train the conditional GANs models, it was generating 10,000 of pairs of corresponding clean, dirty, and horizontal aligned text images of different families, font, and sizes. The image be robust to scale, for instance. And to evaluate the performance of the models, we generate another 10,000 of samples with common distortions. For real data, we evaluate the models via visual inspection analysis. For that, we extract some snip of some data set that in the History American newspaper and the Brazilian thesis repository. Also, here we have on the left some examples or corresponding image with deformation. On the right, we have in the data set the corresponding clean version of this image. Other example that of the transformation, the fact that we include in this image Gaussian noise with rotation, text blurred, and blurred text with rotation on some more cases. To evaluate the performance of the model, we use three metrics: the character error rate, and the word error rate, and the sequence matchers. The character error rate measure the error in terms of characters, and in the case for the words, he measured the error in terms of words. The sequence matcher is the accuracy metric. As a result, here we have the result, the performance in the synthetic data set that we generate from our baseline that is correspond to the tesseract without any preprocessing step. You obtain the higher values in error and the lower values in sequence matched performance. After performing a text alignment,
Okay, you're back, Jose. But we can't hear you. We can see the presentation. Jose, we can't hear you. Rifare un refresh di nuovo. I think you need to do a refresh. Because we lost both the sound and the video. Okay, your microphone. Okay.
I don't know what happened. Strange. I don't know what slide I was presenting.
Just go quickly through. Here we go. Number 25.
25, okay. So we're talking about the performance of our model.
1 minute left, okay?
Okay. We're talking about the performance of the models. In the case, the best result we obtained using the test-cleaner model, where the error was reduced to almost 50%, corresponding to the other best performance that we already have. Well, some example of visual inspection analysis. Here we have some snip of American newspaper, and the right we have the corresponding image after processed by the text cleaner net. You observe that the processing reduce some deformation at the background and improve the quality of the text. Here also in the Brazilian test, we observe that the blur presented on the text was reduced a lot. So a conclusion was proposed the pipeline for text image enhancement based on generative models to improve the tesseract performance. It was demonstrated the capability of conditional generative model to enhance the image quality, and the experiments performed on actually scanned documents consistently showed improvement visually. Thank you. So.
Thank you very much, Jose, for your very interesting presentation. Are there any questions? No questions. Thank you very much.
Okay, thank you.
Thank you. And finally, last but not least, the last presentation of this session. The floor is yours.
Yes, so can you hear me?
Oh, perfectly. Nice and clear.
So I'm sharing the screen.
Okay.
Is it fine?
Yes. And it's already in full screen, okay?
Yes, yes, it is.
Okay.
So hi everyone. My talk is about adaptive regularization methods under in-exit evaluations for non-convex optimization and machine learning applications. The reason why these methods are often considered in place of other globalization strategies, such as Newton-type methods embedded into a line search or a trust region, is because their optimal complexity. In fact, a first-order critical point is found in at most big O of the first-order tolerance to the power of -3/2 iterations, instead of the -2 exponent of line search and classical trust region methods. The resulting scheme is somewhat specular to the probably more popular trust region approach, with which ARC shares the use of a model based on the Taylor series to approximate the objective function values in a neighborhood of the current iterate. But it then differs by adding a cubic regularization term and by approximately minimizing the corresponding cubic model to get a decrease of the objective function. In fact, each vector S such that the model at S is lower than the model at 0 gives a reduction of the objective function when moving from xk to the new point xk plus S. This can be done whether the cubic regularizer sigma k overestimates a half of the Lipschitz constant L2 for the Hessian, which is generally unknown and non-trivial to estimate. So the idea is to choose the regularizer adaptively in order to ensure the overestimation property with a prescribed decrease of the objective function values. The basic algorithm works accordingly. We just highlight that the decrease ratio rho k at step 3 corresponds to the ratio between the true decrease of the objective function and the predicted one obtained by the Taylor series truncated to the second order, and decides about the acceptance of the trial point with the following rule. If rho k is not smaller than the prescribed decrease fraction eta 1, then the trial point is accepted, the iteration is declared successful, the regularization parameter is decreased, and we skip to the test for termination. Otherwise, the trial point is rejected, the iteration is declared unsuccessful, and the regularization parameter is increased to try fulfilling the overestimation property at the next iteration. Coming now to the proposal of reducing the per iteration cost of second-order methods, in which at least Hessian vector products are needed, the main idea is to introduce inexactness in function and derivatives evaluations, while preserving optimal complexity and without deteriorating, hopefully, the overall performance of the algorithm. So let us now move on to a more general framework which covers the case of inexact function and derivatives evaluations. Choosing P in 1, 2, and assuming basically the global Lipschitz continuity of the pth order derivative, a P plus 1 regularized Taylor model, so a cubic model if P equals 2, or a quadratic model if P equals 1, is still considered, but employing inexact function and derivatives evaluations denoted by over bars. We require a relative accuracy condition on the minus delta t bar, which is the sum in the Taylor series defining the model including the derivatives, and an absolute accuracy requirement for the function estimates, still measured by the same right-hand side terms. Moreover, choosing the optimality order Q in 1P, the epsilon tolerances, epsilon j, and some optimality radii delta j, we say that a point x is an epsilon delta approximate Qth order necessary minimizer, whether the optimality measure phi at that point is not bigger than epsilon j times delta j to the j over j factorial for j in 1Q. Basically, it means that not significant decrease in the Taylor series can be obtained within a ball of corresponding radius delta j for j in 1Q. Usefully, phi is a non-negative continuous function of x for all j that can be seen as a necessary optimality condition. And for lower orders 1 and 2, it's a more compact way of addressing the classical approximate first and second order optimality conditions. All these changes are reflected by apply the corresponding algorithm, which is the ARCO-PDA algorithm, in which the next set phi on F and on the model are considered at step 1 and at step 2 for the stopping rule of the model, minimization and of the algorithm, while the next set delta TP on F is considered to set the accuracies on F and on the derivatives. It's worth noting that all these quantities have to be accurate enough when used to be affordable. So a check subroutine is run to verify whether the agreements between xset and the nextset quantities are sufficiently small to fulfill the accuracy requirements themselves. Otherwise, the nextset quantities are recomputed. The scheme then achieves the optimal complexity bound of the basic exact arc framework in terms of the worst case number of outer iterations and approximate F and derivatives evaluations. This is what we have, assuming that the accuracy requirements hold at each iteration of the method. On the other hand, practical estimates of F and of the derivatives are not uniquely identified and can be satisfied only within a certain probability. This is the case of non-convex finite sum minimization, in which the objective function is the mean of a certain number of component functions fi, and the inexactness on f and on the derivatives is due to subsample some of these components from a subset of indexes dkj of a certain dimension, which is the so-called sample size. From a probabilistic point of view, the request on the agreement between xset and the nextset quantities can be satisfied in probability, with probability of success at least 1 minus t, providing that the sample size dkj for the approximation of the jth order derivative at iteration k and j equals 0 refers to f satisfies the inequality in the box. As a result, the optimal complexity theorem holds in probability, with probability of success at least 1 minus t bar arbitrarily chosen in the interval 0, 1, providing that the failure probability t for function and derivatives approximations is properly chosen. Nevertheless, this analysis doesn't give any information about the true decrease of the objective function when the accuracy requirements are not satisfied. This motivates a stochastic analysis of the method, aiming at bounding the expected number of steps needed to reach an approximate Qt order necessary minimizer for the first time. We have an ongoing research on that to cope with random function estimates. So far, accurate function evaluations and random derivatives are considered, and assuming the global Lipschitz continuity of all the derivatives in use to build the model, as well as the boundness of the norm of their approximations on iterations with accurate derivatives, we can prove that the potential inaccuracy in the derivatives has only the effect of scaling the upper bound on the expected number of steps needed to reach an approximate Qt order necessary minimizer by a fraction depending on the probability p star of the derivatives being accurate, retrieving a complexity bound. Before concluding, let me briefly summarize a couple of numerical tests within the framework of non-convex binary classification. Starting from the first order version of the method, so p equals 1 on the NIST dataset used here to detect odd from even digits, the employment of artificial neural network predictive models seems to be particularly beneficial to push a little bit down the testing loss at termination, inducing an increase in the classification rate. While a direct comparison between the first and the second order version of the method on the GZ dataset to detect the highly confusable handwritten digits 4 and 9 suggests that the second order version is preferable when looking at the computational effort to decrease the losses and at the loss values at termination. As expected, the sample size for gradient and Hessian approximation changes dynamically through all iterations, remaining for the majority of iterations far below the full sample size, which is never touched, while the sample size for function evaluations grows faster towards the full sample size, unveiling a sort of hierarchy between function first and second order information. To sum up, we have recalled the adaptive cubic regularization approach and tried to mitigate the main drawbacks related to second-order methods, allowing for inexactness in function and derivatives evaluations while preserving optimal complexity from a deterministic, probabilistic, and stochastic point of view. The next challenge can be, for instance, a fully stochastic complexity analysis under random function estimates, and a new perspective could be investigating the behavior of the method under intrinsic noise. So when you can require the right accuracy only if the accuracy requirements fall above the intrinsic noise level. This is the end of my presentation. Thank you so much for your attention.
Thank you to you, Gianmarco, for this presentation, very clear, and you stayed just inside the time. Are there any questions for Gianmarco? There are no questions. So I guess that today it's all, folks. We finished all the last session for the day. And from the sunny of Cagliari, I say, Anno. Oh, thank you. Thank you very much. And I think I'll leave you on for tomorrow for all the nice, lovely sessions that will be tomorrow. And from me, James, and my technical assistant that is on the back lines. Thank you very much and have a good evening. Bye-bye.
Thank you so much. Bye.
Bye.
Bye.